Okay, hi everyone. Okay, I'm going to go ahead and get started. Okay, today we'll pick up on what we started last time, which was the subject of alkenes. Okay, in the petroleum industry, we let a couple more people in here. Okay, in the petroleum industry, alkenes are known as olefins, which means oil-forming gases. Again, this is the structure of an alkene, the orbital structure of an alkene. The double bond consists of a sigma and a pi bond. The carbons in an alkene are sp2 hybridized. They're trigonal planar. The bond angles are approximately 120 degrees. Okay, what this illustrates is that both the CC bond and the CH bond are shorter in an alkene than in an alkane. Okay, this last diagram right here, the electrostatic potential map, this is critical to explaining why alkenes react the way they do. The region of the pi bond is very electron rich, so these will attack electrophiles. Okay, you do not have free rotation in a pi bond. You actually have to break the pi bond in order to convert from cis to trans, for example. No rotation is possible unless we apply very high energy ultraviolet light of about 264 kilojoules per mole. Okay, I'll briefly review elements of unsaturation. Okay, in lab, the first part of November, we're going to look at qualitative analysis of organic compounds. And one bit of information that you might be provided is the molecular formula. Okay, and sometimes a mass spectrometry experiment can provide you with that information. Okay, if you have the molecular formula, you can calculate the elements of unsaturation. And this gives you a clue as to the number of double bonds, triple bonds, or rings. Okay, each time you form a double bond, you lose 2 hydrogens relative to the 2n plus 2 to n ratio. For a triple bond, we lose 4 hydrogens, and that results in 2 elements of unsaturation. Okay, if we calculate that we have so many elements of unsaturation, the calculation alone can't tell us whether those unsaturations are from rings or whether they're from double bonds. We have to rely on other information. Okay, you may recall last time let's back up for a minute, if a hydrocarbon has a smaller ratio than 2n plus 2 to n, okay, that would indicate elements of unsaturation. Okay, for example, propane, C3H H8, that's CN, H2N plus 2. All right, for propene, of course, we're missing 2 hydrogens, so that's 1 element of unsaturation. Okay, same way with cyclopropane. We're missing 2 hydrogens, so that's 1 element of unsaturation. For a compound that contains nitrogen, what you can do is subtract the nitrogen and subtract 1 of the hydrogens. And then you can calculate the ratio of hydrogen to carbon and see how that compares to the fully saturated ratio. Okay, you do that for each nitrogen. Okay, the reason we subtract a hydrogen is because we'll have an odd number of hydrogens if we have an odd number of nitrogens present. Okay, what about heteroatoms? Halogens replace hydrogen atoms, so we can treat halogens just like hydrogens. Oxygen and also sulfur does not change the CH ratio, so we can ignore those elements when we're calculating elements of unsaturation. Okay, this is the IUPAC nomenclature. As much as possible, I'm going to use the newer nomenclature. Okay, so the position indicates the lower number of the double bond. So but-1-ene means that the double bond is between carbons 1 and 2. For a cyclic alkene, okay, we don't necessarily have to indicate a position number, because in cyclohexene, it doesn't matter where I put that double bond, the name is unambiguous. If I say hexene, on the other hand, you don't know which hexene I have, whether it's one hexene or 2 hexene. All right, the double bond takes priority over halogens and over alkyl substituents. Okay, so in this ring, the double bond is automatically between carbons 1 and 2. Okay, so the first one is 1-methyl cyclopentene, and the second one is 3-methyl cyclopentene. Okay, so if this carbon down here at the bottom, if this is 1, then this is 2. Okay, we can't change directions. If we have 2 double bonds, that's a diene. If we have 3, it's a triene, and we need to locate each one. Okay, we may see examples of alkenes as substituents. Okay, so this is a methylene. So that's 3-methylene cyclohexene. And this is a vinyl group, or sometimes called an ethenyl. More commonly, it's called a vinyl. All right, cis-trans or geometric isomerism. This results from the fact that we don't have free rotation about a double bond. If there are similar groups on opposite sides of the double bond, the alkene is trans. And not all alkenes will show cis-trans isomerism. All right, this would be transparence. This is transistors. And this one is transcendental. Okay, for cyclic alkenes, Okay, we went over this last time, but for smaller rings, the configuration of the double bond has to be cis. The smallest alkene in which you can have a trans double bond is an 8-membered ring. Trans-cyclooctene is only marginally stable, but for larger alkenes, such as cyclodecene, the trans isomer is actually the more stable isomer. Trans double bond, for example, in cyclohexene is impossible. Okay, E and Z nomenclature, we went over this in the lab exercise. We apply the same priority rules as we do for R and S. We compare these two. Okay, this is the higher priority, bromine, and then on this side, carbon is the higher priority. Okay, these are on opposite sides. The higher priority groups are on opposite sides. So that is E. Okay, to convert this to Z, we could switch these two or these two, but not both. Okay, we can have E and Z with cyclic structures. Okay, if we have multiple double bonds, this is how we indicate the configuration. 3Z, 5E, 3-bromo, octa, 3,5-die. Okay, notice we list the position numbers twice. Okay, both with respect to the configuration and with the locants. Okay, we did not cover this last time. Okay, this is the commercial uses of ethylene. Okay, besides the uses that are listed here, ethylene is a natural product. It's produced by a number of plants, and it is a small molecule that regulates ripening. When fruit is shipped for long distances, it's picked while it's still green, and then when it arrives at its destination, it can be exposed to ethylene just before it's to be sold. There are products on the market now. One is called green bags. You can store your produce in green bags, and that has a material that absorbs ethylene, and so you can keep produce much longer because ethylene also promotes over-ripening or spoilage. Okay, another source of ethylene, of course, is petroleum and natural gas. Okay, so in the middle we have ethylene. We can polymerize it. Okay, that is, we can join many thousands of these ethylenes together to get polyethylene. Polyethylene is a form of plastic. It is found in plastic milk cartons. Okay, that's a straight chain. There's also some other varieties. There's branched polyethylene, which is more flexible. You find that in sandwich wrap, for example. There's cross-linked polyethylene, which is much harder than the straight chain or high-density polyethylene. Right, ethylene can be oxidized to acetaldehyde and then to acetic acid. We can make ethylene oxide. Okay, this functional group is called an epoxide, but it's actually a type of ether. It's a cyclic ether with a 3-membered ring. Okay, so this is ethylene oxide, and when ethylene oxide is subjected to acid hydrolysis, splitting with water under acid conditions, we produce ethylene glycol. Ethylene glycol is is a major component of antifreeze and coolant that's used in cars. Okay, we'll talk more about ethylene glycol in our chapter on alcohols. Ethylene can also be converted to ethanol. And ethanol is, of course, a fuel and a solvent. The other way to produce ethanol is by fermentation of sugar using yeast. Okay, we can make vinyl chloride from ethylene, and vinyl chloride is a starting material to make polyvinyl chloride, or PVC. PVC is used to make plastic water pipes. It's also used to make raincoats, for example, and the old phonograph records were made of vinyl chloride, or I'm sorry, polyvinyl chloride. Okay, these are some of the uses of propylene or propene. Okay, we can make polypropylene. Okay, where we string thousands of these propylenes together. Okay, this is like polyethylene, except we have a methyl group on every other carbon on the chain. You would find polypropylene in the containers that you get prescriptions medicines in. Also, yogurt and cottage cheese containers are made of polypropylene. They also use polypropylene to make rope. Okay. Propylene can also be used to make isopropyl alcohol, okay, what we know is rubbing alcohol. It's also a useful solvent in the laboratory. Isopropyl alcohol, of course, can be oxidized to acetone. Besides our use in the laboratory of acetone, this also has use as a solvent in painting. Okay, there are many glues and adhesives and so on that use acetone as a solvent. Okay, going this way, we can convert propylene to propylene oxide and then to propylene glycol. Propylene glycol, okay, let me back up one, like ethylene glycol, is also used as an antifreeze and coolant. It is largely replacing ethylene glycol. Propylene glycol is much less toxic, and it also has some other uses. In fact, it's even used in the food industry, whereas ethylene glycol is extremely poisonous. One use of alkenes, as we've alluded to, is polymerization. Okay, this is one type of polymer. This is called addition polymers. And what characterizes addition polymers is that all of the monomer units are the same. Okay, so here we have polypropylene, polyvinyl chloride, or PVC. And this is polytetrafluoroethylene, which we know is Teflon. Okay, the characteristic of Teflon is that in the bulk phase, it's very slippery. And it's also chemically very inert. The carbon-fluorine bonds are very strong, very hard to break. So Teflon is very unreactive. We have stoppers and stopcocks for our laboratory apparatus that are made of Teflon. They're very Teflon is very resistant to strong acids and bases and oxidizers and organic solvents. Okay, let's look next at the physical properties of alkenes. Okay, so propene has a slight dipole moment. So does cis-butene. Trans-butene, though, has a zero dipole moment. And as a result, it has a slightly lower boiling point than the cis-butene. Right, cis-alkenes have a greater dipole moment than trans-alkenes, so they will be slightly polar. And the boiling point of cis-alkenes will be higher than that of trans-alkenes. Okay, in some cases not by much, but it will be higher. Most of the physical properties of alkenes are very similar to those of alkanes. That is, they're nonpolar or slightly polar compounds. Their boiling points are similar to the corresponding alkanes. As the number of carbon atoms increases, the boiling point goes up. Those that are liquids at room temperature are less dense than water. Okay, we're going to be talking about stability of alkenes. And one way that we can actually quantify the stability of alkenes is by something called the heat of hydrogenation. Okay, we can actually use a calorimeter to measure the heat that is evolved during hydrogenation or addition of hydrogen. Right, this is an exothermic reaction because the two sigma bonds are stronger than the pi bond that is broken, as well as the bond between the hydrogen atoms. Okay, so when we convert but1ene, which is a monosubstituted alkene, to butane using hydrogen, this requires a platinum catalyst. Okay, that is exothermic by 125.9 kJs per mole. Trans-2-butene, okay, which has more substituents on the double bond, and it's also a trans isomer. Okay, that has a heat of hydrogenation of negative 114.6 kJs per mole. Okay, so since the heat of hydrogenation is less, that indicates that the original alkene was more stable to begin with. Okay, so more substituted double bonds are usually more stable. All right, so here we have a table of various alkenes. Ethylene is included up here at the top. And if we have a monosubstituted alkene, it doesn't really matter too much what R is, whether it's a butyl or an isopropyl or an isobutyl or whatever it happens to be, or whether it's 10 carbons. Okay, the nature of the R group doesn't make too much difference. Okay, so that's going to be more stable by 11 kJs per mole compared to ethylene. Okay, if we have a disubstituted alkene, okay, where we have more than one R group on the alkene group, Okay, it depends on whether the dye substitution is cis, geminal, or trans. Okay, if it's cis, it's more stable compared to ethylene by 18 kJs. Geminal, where the two substituents are on the same carbon, then it's 19 kJs more stable, and then a trans is 22 kJs more stable. Okay, a tri-substituted is more stable than a di-substituted, and a tetra-substituted is more stable yet. Okay, this is an important idea. A ring makes a major difference only if there is ring strain. Okay, either because of a small ring or because of a strained trans double bond. Right, rings that are 5-membered or larger can easily accommodate double bonds, and these cycloalkenes will react much like straight chain alkenes. Okay, but if we have a 3 or 4-membered ring with a double bond, okay, that's going to be more reactive because of ring strain. Okay, we can see the difference here between cyclobutene and cyclopentene. Okay, negative 129.7 versus negative 112.7. Okay, cyclopropene is very highly strained. Okay, we talked about cyclopropane earlier, where tetrahedral carbons, which have an ideal bond angle of 109.5, are forced into 60-degree bond angles. With cyclopropene, we have sp2 carbons, which are forced into 60-degree angles, okay, from the ideal of 120. Okay, so this is very highly strained. Surprisingly, there are some natural products. There's a tropical plant, for example, that actually has a cyclopropene ring as part of its structure. Okay, so here's a little bit more about cycloalkenes. Okay, if we have a trans double bond, trans-cycloheptene is marginally stable. It's actually fairly difficult to build a model of trans-cycloheptene. Trans-cyclooctene can exist. You can build a model of it. The cis isomer is actually more stable for cyclooctene. And as I mentioned earlier, for cyclodecene and larger rings, the trans double bond is almost as stable, in some cases more stable than the cis. Okay, this is something called Brett's rule. Okay, back a few chapters ago, we talked about bicyclic compounds. And here we have an example of a fused bicyclic compound on the right. And on the left, we have an example of a bridged bicyclic compound. Okay, the difference is that for a bridged bicyclic compound, you have at least one carbon in all 3 of the rings. Okay, so the systematic name for decalin would be bicyclo-440 decane. For norbornane, it would be 221 heptane. Okay, so we have at least one carbon in each one of the bridges. Okay, so how does this relate to alkenes? Okay, for decalin, which is a fused bicyclic compound, okay, these are the bridgehead carbons right here. Draw this twice. Okay. We can put a double bond at the bridgehead. Okay, I can easily make a model of this. I can easily make a model of this. Okay, these are stable, they can exist. There's no problem. Let me go ahead and erase this. Let's compare that to the bridged bicyclic compound. Okay, for this, it is not possible to have a double bond at one of the bridgeheads. Okay, so this would be impossible. All right, this would be impossible. And you can prove that using models. Okay, you can't build a model of these compounds. They would be prohibitively strained. Okay, if we have a double bond not at the bridgehead, make sure I'm not off screen. Okay, if we have this, where the double bond is not at the bridgehead, that's okay. Okay, but you can't have a double bond at the bridgehead unless one of the rings has at least 8 carbon atoms. Okay, here, okay, this ring has 6. This one has 5. We go around this way. Okay, so the rings are too small. Okay, so the question is asking, and I've actually answered a couple of these. Okay, part A, that alkene is stable. Okay, since we don't have a carbon in all 3 of the bridges, we've got a 0 carbon bridge. Part C, I just gave that example. That one is stable. The double bond is cis, so that one's okay. Okay, compound B, okay, would be impossible. Okay, because that's a 6-membered ring. We've got a double bond at the bridgehead, so that one could not exist. Okay, compound D. Okay, we have a large enough ring. Okay, the ring on the bottom has 8 members, and so that one is possible. Okay, so that one could exist. Okay, we're gonna look at alkene synthesis next. Primarily, the way we obtain alkenes, if we don't have an alkene from a natural source, is from either halogens or alcohols. Those are the 2 primary sources. And these involve what are called elimination reactions, where we remove 2 groups from adjacent carbons to obtain a double bond. Okay, so we're going to look at dehydrohalogenation. Okay, that's where we remove a hydrogen and a halogen from adjacent carbons. We can do dehalogenation, where we have a vicinal dihalide. Okay, remember that's where we have a halogen on each of two adjacent carbon atoms. We can also do dehydration of alcohols, where we remove an H and an OH. All right, so here we have two types of dehydrohalogenation, and these are classified as E1 and E2. Okay, notice that we don't use subscripts here. Okay, unlike the SN1 and SN2. Okay, so the first one is the E1, and it starts out just like an SN1. Okay, the first step in an SN1 is ionization. Okay, also called heterolysis. Okay, both these electrons go to the bromine. That leaves a plus charge on the carbon. In the SN1, the solvent would then attack the carbocation. But here the solvent is removing this beta hydrogen. A pair of electrons in the CH bond then moves toward the carbocation, and that gives us this alkene. Then we have a protonated methanol. Okay, the other limiting case is what we call an E2. Okay, remember that the SN1 occurred in two steps. Okay, just like the E1. The E2, the E2, like the SN2, occurs all in one step. Right here, CH3O- is a base. It takes that beta hydrogen, the hydrogen on the carbon next to the one carrying the halogen. Okay, it pulls that off. The pair of electrons in the CH bond moves toward the adjacent carbon. At the same time, it pushes out the bromide. Okay, so there's no intermediate in the E2. There's just one step. The E1, okay, like the SM1, is a unimolecular elimination reaction. There's two groups that are lost, the hydrogen and the halide. The nucleophile acts as a base this time. When we say a nucleophile is acting as a base, it's attacking a hydrogen rather than a carbon. E1 and SN1 have the same conditions, so we can get a mixture of products. Okay, so this is how the E1 occurs in general. We have ionization, and then the solvent removes this beta hydrogen and forms a double bond. Okay, the first step, the ionization or the heterolysis, is a slow step. So that determines the rate. Right, so after the heterolysis or the halogen leaving, okay, we have some overlap here between this sp3 orbital and the empty p orbital, which helps stabilize the transition state. And once the base removes this hydrogen, then you have the overlap occurring to form the pi bond. Right, this is the E1 energy diagram. It actually looks similar to the SN1. Okay, you have the first step, ionization. This is an intermediate, this local minimum. The second step occurs rapidly. Okay, and the base and the halide are no longer attached. Okay, otherwise you'd have too many bonds. Okay, next we'll talk about Zaitsev's rule. Okay, Zaitsev was a Russian chemist during the 1800s. He was a contemporary of Mendeleev and several others. And this rule says that if more than one elimination product is possible, the most substituted alkene or the most stable alkene is the major product. Okay, and earlier we talked about what constituted a substituted or more stable alkene. Okay, so here we have a carbocation. The plus charge is on the second carbon. Okay, these 6 hydrogens here are all equivalent. These 2 beta hydrogens are different. Okay, we want to look at the next carbon over to locate the beta hydrogens. Okay, so there's 2 possible alkene products that could be formed. Okay, so the solvent could take away this hydrogen and we form the double bond here. And of course, forming it here would give us the same product. Or it can remove this hydrogen and we form the double bond here. Okay, since 2-methylbutyene is more substituted, it is the major product. Okay, and experimentally, it says that this is formed in 90% yield, and the other one, the minor product, is 10% yield. Okay, so the first one is tri-substituted, and the second one is di-substituted. Okay, so the more substituted alkene will be the major product. Okay, you can see that we get both of these products, but we can predict which one is going to be the major product. Okay, and Zaitsev's rule works the way it does because we get the more stable alkene. Right, in this example, we get a tetra-substituted versus a di-substituted. And of course, we would predict that the tetra-substituted alkene would be the major product. Okay, next we're going to move on to the E2 reaction, the other type of elimination. The E2 is bimolecular. Okay, this does require a strong base. Okay, for the E1, we could use a weak base, ethanol, and earlier we had an example of methanol. Those are weak bases. Water is also a weak base. Okay, but this one you have to have a strong base. It's a concerted reaction, which means that bonds are formed and broken all in the same step. Okay, so the proton is removed, the double bond forms, and the leaving group gets pushed out all in one step. Okay, earlier, that is in the last chapter, we talked about how a tertiary halide cannot undergo SN2 because the backside is too crowded, it's too hindered. Okay, but if we have a strong base, okay, this is methoxide, it's the conjugate base of methanol. Since it can't undergo SN2, it turns out it can undergo E2, and it can undergo E2 very readily. Okay, so it removes a beta hydrogen. Okay, we form the double bond, kick out the bromide, and we get this alkene as our product. Okay, this is second order kinetically. It depends both on the halide and the base concentration. Okay, it's also bimolecular. Okay, because the base and the alkyl halide are both involved in the transition state. Right, the order of reactivity for alkyl halides, okay, is quite different. In fact, it's the opposite for E2 compared to SN2. Okay, for SN2, we said it was methyl, primary, secondary, and then tertiary doesn't happen. For the E2, it's tertiary, secondary, and primary. Okay, I don't have methyl listed here because with a methyl halide, okay, such as bromomethane, you cannot form a carbon-carbon double bond because you only have one carbon. Okay, a mixture may form, but the Zaitsev product predominates. Okay, the Zaitsev's rule applies to both the E1 and the E2, and the order of reactivity is actually the same for the E2 versus the E1. Okay, the difference, again, is the base, and of course how the reaction occurs. E2 has to have a strong base, E1 uses a weak base. Okay, if we have a primary or secondary alkyl halide, okay, that's usually going to be prone to SN2. However, we can often force an elimination, and we can also force what is called the Hoffman orientation by using a bulky crowded base. Okay, so this is so O minus is the basic atom. Here it's nitrogen, nitrogen again, nitrogen. Okay, so it's very crowded around the atom that's abstracting the base. So these are called bulky bases. Okay, so what is the Hoffman orientation? It's just the opposite of the Zaitsev orientation. That is, the less or least substituted alkene will be favored if we're using one of these bulky crowded bases. Okay, so here's an illustration. Okay, so we've got 2-bromobutane. We've got 2 sets of beta hydrogens. We've got these 3 that are color-coded in blue and these 2 that are color-coded in green. So we can get 2 alkene products. Okay, ethoxide in ethanol. Okay, this is an uncrowded base, and so it's going to go for the more substituted product, the Zaitsev product, whereas tert butoxide is a bulky base, and it's going to go for the less substituted. You can see that the product ratios are almost the same, but they're opposite. Okay, so with the uncrowded, unhindered base, we get the more substituted. With the crowded base, we get the less substituted as our major product. Okay, I have about 1 minute remaining, so I'll just mention this. We'll pick it up next time. For the E2 reaction, the stereochemistry is very important. The hydrogen and the halogen have to be anti or 180 degrees to each other for this to occur. For the E1, doesn't matter. Okay, so I'm going to go ahead and stop there. And I will see you on Monday.
Dr. Trump?
Yes.
I was doing my online homework, and on one question where we have to draw the Lewis structure,
Okay.
it's not accepting the answer, and it says that try again, and if it doesn't work, contact the instructor. I tried it again, and it's not working. Let me tell you which question is that.
Okay. If you're on campus, you can stop by. Otherwise, I can set up a Zoom for you in a few minutes. But I'm going to go ahead and end this meeting for everyone else. Does that work?
Sure.
Okay. Are you on campus?
Oh, no. Can we have a Zoom meeting?
Yeah, I can set up a Zoom, and I'll send you an invitation.
That
Dr.
sounds
Tom,
good.
I also had the same issue with the question not submitting.
Okay. This is Sonia.
Yes.
Okay. All right. Um, okay. Tell me what question it is.
Okay, it's chapter 4, question 2, part B.
Okay. I'll check that out.
Yeah.
Yeah.
Also, I was wondering if there is any chance that you can extend the date by day or two. I'm like,
Probably.
because, oh, sorry.
Yeah, I probably could do that.
Yeah, because the drawing structure, the Lewis structure, it's just not accepting it, and I haven't done it before. So I'm just like struggling with like what specific structure it's accepting. So probably we can solve that during the Zoom session.
Okay. Yeah, I'm going to go ahead and end this meeting, and I'll send you and Sonia a Zoom invitation, and we'll have a look at it.
Sounds
Okay?
good.
All right.